Good morning, and welcome to the Museum of the San Ramon Valley's virtual speaker series. I am Dan Dunn, the director of the museum. Last time, John Martini told us the story of the bridge that couldn't be built, now the symbol of the Bay Area, the Golden Gate Bridge. Today, the insides of another symbol, Mount Diablo. For the residents of the East Bay, the mountain is considered their mountain. It helps us to orient ourselves to our area. Don Medvedev will discuss the geological makeup of the mountain, from its origins, fossil past, and unique ecosystems. Discover the wonders of this unique landscape. We got a good guide this morning. Don received his BS, Master's in Science, and PhD degrees in Geological Science from the University of Michigan, Queen's University, and Princeton. As part of his studies, Don has analyzed the geology of the Southern Appalachians, the Canadian Rockies, and the California Coast Range. After university, Don has held positions in technology for 30 years at ARCO and Chevron. Since retiring in 2017 and living in Danville, Don has studied the geology of Mt Diablo and the greater Bay Area. Please use the chat window at the bottom of the screen for any questions that you have. Feel free to send in questions at any time during the presentation, and we'll address them at the end. And now it's my great pleasure to welcome in Don Medvedev. Don?
Thank you, Dan, for that introduction. And as Dan alluded to in his presentation, Mount Diablo really is a pinnacle landmark in the East Bay, in particular, in the Bay Area in general. And that's illustrated at the illustration at the base of this slide, which is a sketch made during the 1850 American River Expedition, which just goes to show how long the mountain has been a landmark for those of us in the Bay Area. I've divided my talk today into 5 sections. Since many people may not have studied geology since high school, I put in a section I'm calling Geology 101, where I'll talk about the basics of geology, just to provide us a common terminology and understanding of the Earth that we can use to apply to Mount Diablo. Next, I'm using the first really professional observations of the mountain that were made during the Whitney survey in the 1860s. And that is a great way to think of the mountain, because these are folks who wouldn't have today's modern geologic knowledge, but they had basic geologic knowledge, and they were made exceedingly good observations, the same kind of observation you can make today when visiting the mountain. Then I'll present a geologic map of the mountain and talk about the different rocks that are found in different parts of the mountain. And then I'll go through a modern understanding of the geologic history of the mountain. And finally, I'll end with a slide presenting you with a series of sources where you can find more information if you have continued interest in the geology of Mount Diablo and indeed the region, Bay Area region. So first, what is geology? What are the components of the study of geology? And I break that down into 3 basic components: a descriptive component, of geologic processes on Earth, and the history of this unique planet that we live on. So in terms of description, what rocks are where? That's a sort of fundamental thing to know. You go around the world and you look in the ground and on mountains, and you see what rocks are where. And it turns out different rocks are in different places. And to document that, geologists, I guess starting in about the earliest 1800s, started making maps of what rocks were where. And this is a recent map of the geology on Mount Diablo. You can see the Southgate Road here going up to Junction, and the Northgate Road coming in from the west, and they coalesce and make the Summit Road to the top. And the different colors illustrate, in this case, the age, the time of origin of different rocks on the mountain. Another thing to consider is, well, what are rocks made of? Rocks, I guess the fundamental definition of rocks is that they are solid components of the earth that are composed of minerals, and minerals themselves are naturally occurring crystalline substances. And so we have a variety of different rocks made of various minerals. Minerals can either precipitate from a solution, primarily rock salt and something called sylvite, which is potassium chloride. But most minerals form by either crystallizing out of a melt, as this granite here in the upper left, or being later altered by minerals that formed in some other way. And then another question, really fundamental in the history of geology is, well, what can we do with these rocks? What has really, over the centuries or millennia even, spurred people to study the earth is to find useful resources. And on some of those that we can find on Mount Diablo are, first of all, coal, which is sort of one of the few organic rocks because it started its history as plant material in this case. And that has been used for centuries now as a form of energy as well as industrial processes. Another resource on Mount Diablo is sandstone, which in very pure form, when it's pure quartz, is economic or has been economic in the past to make glass out of. And there are still today, you can find on eBay, glass bottles that were made from the sand at Mount Diablo. And really the only continued resource, natural resource being used at Mount Diablo today is what's called aggregate. These are very strong crystalline rocks that are found on the north side of the mountain near Clayton. And those rocks are quarried to form building materials for road beds, as well as foundations for walls, and as mixture into concrete. Rocks, as I alluded to earlier, formed by different processes. And this diagram, which I took from a U.S. National Park website, talks about the rock cycle. And this particular rock cycle is very pertinent to the west coast of North America and California in particular, because as the Pacific Northwest coast today, so was the rest of the North American coast for about 100 million years previous to that, where we had oceanic rocks that were being subducted or thrust underneath the continental lithosphere. And lithosphere is just the rock portion of the earth. And this oceanic lithosphere formed at what are called mid-ocean ridges, either by eruption of volcanic material or the same magma source crystallizing at depth. And as it moved away from the mid-ocean ridge, these volcanic and plutonic rocks were covered by sedimentary rocks, first by siliceous oozes. These are the crystalline shells of microscopic organisms that accumulated very slowly over millions of years and created a thin veneer on the crust. And then later, as the lithosphere approached land masses, they were covered by shales, mud, and then eventually sand very near the continent. And these rocks then subducted under the continent and melted and formed volcanoes, which were created the Sierra, an earlier version of the Sierra Nevada. And then erosion of the Sierra Nevada created more sandstones. And we see all of those features at Mount Diablo. And another aspect of geology, which really makes it relatively unique amongst the sciences, is the historical aspect. Physics, for instance, studies really fundamental properties. Here in geology, we study both fundamental properties, but also how those properties have borne out through time, creating a unique and characteristic story in different places. And here is a map, a reconstruction of what Western North America and California in particular would have looked like 50 million years ago, which was the time for the deposition of the sandstone, which you can find at Rock City today. So rather than being completely inland then, the area of Mount Diablo was in an inland sea with a deep water basin being fed sediments from the east. So I alluded to rocks being crystalline substances, but we commonly find rocks in layers. And here's an example of two types of rocks that are created in layers. In the upper right is an image I took a few years back in Western Australia, near the town of Broome, where there's very large 30-foot tides, which allow us to see the seabed when the tide is out. And here we see a very clean sandstone that's been eroded from the interior of Australia, creating very gently sloping sand, which may eventually turn into sandstone. In the lower right image, we see, this is actually taken from the web, a picture of Iceland just a few weeks ago, where recent lava flows are flowing out across the plain. And although lava flows are locally rough, in broad perspective, it creates a very flat and nearly horizontal form. And this also begins to illustrate two of the three different types of rocks. We have sedimentary rocks, we have volcanic rocks, and the third is harder to picture. The third is what we call metamorphic rocks. And these are rocks that started life as something else, but were buried and deformed and heated and altered in form, hence the name. So as we just showed, those many rocks form as horizontal layers, and you can see here in the Grand Canyon, we see horizontal layers dating from prior ages. But unlike the last two images where the rocks were near sea level, these rocks are up to 7,000 to 8,000 feet in elevation, or 2.5 kilometers above sea level. And that's not where those rocks started. They started either below the sea or very near sea level. And so something has happened to elevate those rocks. And we have a rule of thumb in geology called original horizontality. So if the rocks are not horizontal or not near the elevation they were formed, then some process has occurred to elevate them. And that is how we start working out geologic history. The slide in the lower right shows these are actually limestone rocks. This is from the Austrian Alps. And here the rocks have not only been uplifted, but they've been folded here into a U-shaped form, which we call a syncline. Cline from the word Latin for dipping, inclined, and syn meaning together. So the beds dip together. And if beds dip apart, we call that an anticline. In fact, Mount Diablo at some scale is a very large anticline. And these deformations, the deforming rocks from horizontal and sea level to different elevations and different shapes, is deformation processes. And in the earth, these can happen at a variety of scales, from meters to thousands of kilometers, really. And the difference is really how deep these processes. The very deep processes generally create large structures. Shallow processes, such as landslides, create very small structures. So now that's the end of the Geology 101 lecture, and now I'm going to go into some observations made by the Whitney Survey of California. The Whitney Survey ran between 1861 and 1864, and it was a child of the early California legislature. They wanted to have a better knowledge of the geography of California and the geology of California that they could use to basically find out where gold and other resources were, so that the state could plan for that. And perhaps the legislature could get it on the ground floor. So a guy named Josiah Whitney, who was a Yale-trained geologist, was brought in to lead the survey, and he was the state's first state geologist. But Whitney spent most of his time in San Francisco and Sacramento dealing with the politicians. And a man named William Brewer, I should say before I move on, this is a picture of the Whitney Survey camped in front of Mount Diablo. You can see in the distance there. And I believe that was dated from 1861. And you can see there, this is probably the highest tech they had in terms of moving across the state. But as I said, Whitney didn't travel with the survey very much. It was led by William Brewer, was the party chief. And he was also a Yale graduate, but in chemistry rather than geology, with some additional training in Europe in geology and chemistry. And his real passion was actually for bringing science to agriculture. And he eventually, at the end of the survey, went back to Massachusetts, where he got a faculty position in, I guess we would call it agronomy today. So the Brewer and his crew, which varied through time, traversed California on foot, on horseback, using mules, and even occasionally steamer from 1860 to 1864, which is, of course, right during the Civil War. And while doing so, he wrote his brother back in Massachusetts stories in letters of what was going on. And those letters were later compiled, I think, in the early 20th century as a book called Up and Down California, which you can get perhaps at your local bookstore, but certainly on Amazon. And it's now in its fourth edition. And I recommend the fourth edition because the fourth edition has maps showing with the modern geography of where Brewer and his group went. And you can see with the picture of Brewer here on the left, carrying a barometer. And one of the key things they did was to map out the geography of California, hike up many of the mountains, including Shasta and some very high mountains in the Sierra, and using two barometers, one at the base of the mountain and one carried up top, to determine the elevation of mountains, including Mount Diablo, which he walked up multiple times. So I have some quotes out of Brewer's journal / Up and Down California. So here's one dated from 1861, writing from San Francisco. He says that Mount Diablo is a bold peak, nearly 4,000 feet high, which is accurate, and it's one of the most extensively seen objects in the state because of its central position and the great distance that it's visible from. A point at the top is used as a starting point of all surveys in the state. And that was true then, and it's true today. On the left, I brought up a geographic map, a topographic map of the mountain, and overlaid it in red with the modern survey, which is, you can find on Bureau of Land Management site. And as you can see, the center of the top of the mountain is the center of the grid, with one north, one west being in the upper left corner, and one south, one east being in the lower right corner. And spreading out from there all the way up towards Mount Lassen in the north and down south of Bakersfield in the south. Brewer also mentioned in his journals the story of how the mountain got its name, this story which you've probably all heard, that the Spanish were had a battle with the Native Americans that had escaped their enslavement. And during that battle, the devil came out to either help the Indians or help the Spaniards. I've heard different versions of that. And Brewer, leaping from that, says the rocks certainly do look as if the devil had been about them sometimes. There is a breaking up and roasting of the strata on the grand scale. And here on the left, you can see this is a picture from the Summit Road showing chert layers that are dipping vertically here and have been baked, and they're brown and crumbled. And locally, you can see many faults in them. So Brewer's observation was spot on. Brewer, now writing from Clayton a few weeks later, and when he writes from Clayton, he actually talks about Mr. Clayton and his ranch. So he was there at the beginning of what we know as Clayton. He says the strata about Mount Diablo are of the most enormous thickness, not less than 1.5 or 2 miles thick, with the elevation meaning he meant the uplift of the mountain. These layers were broken up, and the central mass, that's the core of the mountain, was roasted and baked, and the broken edges stuck up, forming ridges 2,000 feet high, the strata dipping at high angle. And so I have a picture here on the upper left, which is I've taken by a screenshot in Google Earth, looking obliquely northwest from the Tasajara Valley. We can see these layers striking northwest, and this would be several kilometers thick just right here on the southwest side. And the strata are even thicker, it turns out, on the east side. This image in the lower left is some Cretaceous sandstones, and this is taken from the Burma Road just north of Juniper Campground. If you head north from Juniper Campground, there's a fire road there, and it has these Cretaceous sandstones, which again are highly deformed and they're rusted looking because they've been altered, which is what Brewer meant by roasted and baked. And finally, the lower right image is from the Mercedo Ranch area, the China Wall area, if any of you are familiar with that. And we see here Miocene sandstones that are rotated or tilted to vertical, which you can tell because these lines, the layers go straight up the hillside, which means that the beds are dipping almost vertically. If they were inclined at a gentler angle, they would have a V shape in the valley, but here they go straight up. And finally, finally, I guess that Brewer also commented on the many fossils and coal layers on the mountain. And he said they saw one that was over 4 feet thick with the beds in a strata which is found being inclined about 45 degrees, which is how they are dipping on the northeast side of the mountain. And they apparently found a piece of wood that was only partially decayed within a layer of clay, and that wood was 6 feet long. And they managed to dig out a 16-inch piece of it, which they described as being quite perfect with the knots. And it seemed like the piece of wood might have lain just a few years in the wet mud, partially rotted, but yet the rest sound. And then he was amazed. He said this lay in a stratum that must have been nearly a mile, with nearly a mile or so of rock deposit over it, which was then rotated up with the raising of the mountain. And then his final quote here is just, the mind vainly tries to grasp the ages that stick must have been thus buried. Because of course, in Brewer's day, although geology was beginning to be understood, the actual time involved was not at all known. Throughout the 1800s, what we call the geologic timescale was developed. And Brewer was probably aware of some of this, but it wasn't fully developed at the time. And but by piecing together rocks with different fossils in them and observing which rocks were on top of others, geologists throughout the 19th century were able to create this timescale at which they labeled old life at the bottom, the lowest rocks, middle life, and then the youngest or new life on top. And then within those divisions, there were additional subdivisions, again, based on different fossil types. Beginning in the early 20th century, radioactivity was understood, and some clever people were able to observe that radioactive decay started in certain minerals when they were formed, and by looking at the ratios of the parent product to the daughter product of those particular elements, you could determine the number of years that had passed since the mineral was formed or crystallized from the melt or cooled below a certain temperature. And by applying that technology to the already identified geologic timescale, geologists and geophysicists were able to put actual dates onto in terms of millions of years. So MA here is millions of years and thousands of years. But to provide, if I just tell you that such and such rock at Mount Diablo is 100 million years old, it really won't mean so much without context. So I'm going to present some context. So here on the right are some images from the Grand Canyon, which is a famous place of geologic exposure. And at the very base of the Grand Canyon, there are rocks that were deformed into their current state about 1.5 billion years ago. And those are the oldest rocks exposed on the Grand Canyon. And we call that time Proterozoic, so pre-life or early life. And on top of those rocks, starting with the Cambrian Revolution or just before, are some of the old life. And those rocks are 590 to say 400 million years old. And then the upper part of the Grand Canyon, the rocks are younger because the younger rocks are deposited on the older rocks. And they're in the order of 350 to 270 million years old, the top of the Grand Canyon. So mostly Paleozoic rocks. If by contrast, one goes to Zion National Park, we see younger rocks. The oldest rocks at Zion are about the same age as the youngest rocks in the Grand Canyon. And then there's a whole series of sandstones with some limestones representing deserts and shallow seas that formed mostly during the middle life period, Jurassic and Triassic. And so these rocks range in age from about 270 million years to say 100 million years old. So that's some context. And then we're going to go to Mount Diablo. So again, my image taken from Google Earth with the different rock layers here. And what we have at Mount Diablo, the oldest rocks are in fact the rocks being quarried that I mentioned to you over by Clayton. Those rocks, as it is, turned out to be rocks of oceanic crust that was formed from a melt in the Jurassic time period. So probably 130, 140 million years ago, something like that. Sitting actually unconformably, so not, well, no, I take it back. Sitting conformably on top of those rocks are Cretaceous sandstones. And these range in age from about 110 to 70 million years, I believe is about the top of that sequence there. And then above that, with a gap in time, a significant gap in time, are Eocene rocks, and these are most clearly seen in Rock City area. The big thick sandstones at Rock City are Eocene, and they're 45 to 50 million years old. And then there's another gap in time. The Oligocene is missing throughout much of certainly northern California. Are Miocene rocks, which are again sandstones primarily. And these are the rocks, if you go to Walnut Creek open space and see the fossiliferous, that's shell ridge with all the shells in it. These are Miocene sandstones. And I alluded to earlier geologic map. Here's a Google Earth view with Mount Diablo at the center, looking straight down now, Danville in the lower left, Martinez in the upper right, Brentwood in the far right. And I'm going to now overlay that with a geologic map. And this is a geologic map produced by Tom Dibley and edited actually after his death into a beautiful series of maps, which you can in fact find on the U.S. Geological Survey National Map website. And the basic idea here is that different age rocks are illustrated with different colors. And I've simplified the colors on the diagram on the right because there's more subdivisions here that I can talk to today. And at the core of the mountain, we have Cretaceous rocks, which have been subdivided further with different colors, distinguishing between chert, greenstones, which are altered lavas, and greywackies, which is a dirty sandstone that's been formed. So that's what's observed in the center of the mountain. And then there's actually faults all the way around that. This boundary here is a fault. So we're actually seeing a window into a lower plate with these other rocks on top. And then the deep blue here are the, I'm sorry, I forgot to click the boundary. I wanted to show these different rock types in the Cretaceous. So on top, we have greywackies, which is a sandstone that was deposited in deep water. It has a lot of clay in it. Then in red here, we have these chert bodies, which you'll see also throughout the top of the mountain. And these are layers, as I alluded to earlier, formed out in the deep ocean, far from continental areas, with deposition of radiolarian chert into oozes, which were then later buried deeply and crystallized. And finally, they're actually hard to tell from the sandstones. There are what we call greenstones, because if you get a fresh sample, they are in fact green. And these are original lava flows that have been altered and recrystallized with different minerals, but we can still see the shape And I'll talk about that here. You can see this curved shape. That's what's called a pillow basalt. And so that is diagnostic of lavas that were erupted in deep water where the pressure is too high to allow bubbles to form. And then in dark blue, as I started to say earlier, is the crystalline rocks that form the base of the oceanic crust onto which those other rocks were deposited. And that is the quarry shown in the quarry near Clayton today. The Cretaceous rocks are not so obvious on the west side of the mountain. To see the Cretaceous rocks, it's best to go over to the Morgan Territory area off of Morgan Territory Road. And in that region, Morgan Territory, East Bay Regional Park, where there's several kilometers of Cretaceous sandstones exposed, because layer after layer after layer. And these sandstones were deposited in the prior version of the modern Great Valley. The Great Valley used to extend west at least as far as Rock Ridge and Berkeley, or Oakland rather. So because we find remnants of those rocks that far west, and they're known from the subsurface through petroleum exploration in the Great Valley itself. So here's that diagram again, now colored, where we have the mid-ocean ridge, where we have diabase, which is the rocks being mined or quarried at Clayton, solidifying in the ground in the subsurface so they cool slowly and make big crystals. Lava flows erupting on the base of the seafloor, often creating pillow basalts. And as the rocks move away from the subduction zone, we get first chert deposition, where you're too far from the continent to get any mud or sandstone. And then as you get closer to the continent, first you start getting the mud, which will compact into shale. And finally, in a trench near shore, this would be equivalent to being offshore, say Portland or Seattle today, we get sandstones accumulating. And then there's, in this subduction situation, we have what's called a accretionary wedge, where those rocks are often scraped off the downgoing slab and mixed up. And in fact, the core of Mount Diablo is an exposed version of this accretionary wedge. And then sitting on top of that, we have what's called the forearc basin. It's called forearc because it's in front of the volcanic arc, which in the Western California situation would be the Sierra Nevada, or the volcanoes that used to be in the Sierra Nevada. And with sandstones depositing in the Great Valley today, and then again in the past, the Great Valley sandstone continued farther west. And in fact, what I show here is GVO, the Great Valley ophiolite. That's a fancy word for the crystalline rocks that we see today at the Clayton Quarry, were actually not part of the downgoing slab. They were part of a different piece of oceanic crust on which the forearc basin sat. So it's a complicated scenario of how these rocks were formed. So going back to the geologic map and going higher in the stratigraphic column, younger in time, after the, or late in the process of the subduction zone, we started getting these deep water sandstones, very thick sandstones, pouring west over a now broken up continental shelf. And these are the big, thick sandstones that we see at Rock City that have the wind caves. And you can tell, it's not so obvious here at the wind caves, but if you go just south of that towards Live Oak Campground, you can see this outcrop with these very thick beds separated by a very thin bed. So this flow here, this sand rather, layer was actually accumulated in just a few minutes or at most an hour or two in a big, massive underwater landslide where the sand gets entrained in the water column and then settles out over tens of square miles probably. And so unlike the church that we saw earlier, which formed over millions of years, these rocks, as we're now close to the continent, can form very quickly. And then finally, on top of the Eocene sandstones are more Miocene sandstones, and these now have a lot of volcanics entrained in them, and so they weather quite differently. And this, in the upper left, is an image of the so-called China Wall again at Mercedo Ranch, and where we can see the rock layers are vertical going across the landscape. And in the lower right, this is a similar age Miocene unit, I think slightly younger, that's exposed along the Southgate Road. So if you're bicycling up very slowly, you'll have plenty of time to look at those Miocene sandstones as you bicycle up. So that's the distribution in rock types. But then in terms of how they all got to be where they are, Mount Diablo, unlike, say, the Grand Canyon, has a very complicated history. And quite honestly, it's still somewhat controversial today in details, but the basic picture is well understood. As I said, I'm starting in the lower left here with these are cross sections, so illustrating what the Earth would look like if we sliced it vertically. And we have here the oceanic crust in purple with a layer of, say, chert in green, and then sandstone on top of that. And that's being subducted down into the mantle with bits and pieces of that here schematically shown as being scraped off into blobs, which is not that simple, but something like that. And then with the Great Valley, Forearc Valley sitting on top of it with an older oceanic crust and the sandstones. And then if we, so that's going on from about 120 million years on to, say, 80 million years ago. Then there was a change, and that system got torn apart, and we're now jumping ahead to 20 million years ago, where we have those older rocks which have now been torn apart by faulting, and we have the Eocene rocks being deposited in blue here. That's the Rock City rocks being deposited over some fault blocks underneath, and then and that was at about 40 million years. And then 20 million years ago, we have an extensive period layer of sandstones covering the whole thing. And finally, starting about 5 million years ago, that whole system got redeformed by compression and squeezing, related to the in a general sense, to the San Andreas fault system, which is now allowing the Pacific plate to move north relative to California. And in doing that, the oldest rocks, which were at the bottom of the sequence, have now been thrust up, pushed up on top of Mount Diablo, with the younger rocks being folded about that. And then actually the rocks at the very top of the mountain are actually thrust from the north. So that's a completely separate fault system, putting the rocks of the ophiolite on top of the older rocks. Very complicated history of specific events. So then, like I said, I would end with giving you some ideas on where you can go for additional information or continue your studies of the mountain. The first place I would recommend is the Mount Diablo State Park Trail Through Time brochure, which I gather you can get at the Museum of the San Ramon Valley. You can also get that at the top of the mountain at the Visitor Center. And this is basically a map guiding you through a whole series of diagrams that have been placed on the mountain on a trail that goes from below the Southgate entry station and works its way all the way up to the summit of the mountain. And you'll find signs that talk about the geology in different places. A couple of years ago, the Mount Diablo Interpretive Association, in conjunction with the Northern California Geological Society, put together a map of the mountain that has the latest U.S. Geological Survey mapping by Russ Kramer and others at the survey, along with images of different rock types in different places, and a description of the rocks and a description of the history of the mountain. For those of you who are more into 21st century things rather than old school paper, there's a program that's really unrelated to Mount Diablo, but RockD, all one word, can be downloaded from both the Apple App Store as well as the Android App Store. And this has geologic maps at different scales, I believe, for the whole Earth. some more detailed than others, and Mount Diablo is included. So if you go to the mountain and click on, show me the map of where I am, the map of the different units will come up, and you can click on a location and it will give you a description of the rocks you're looking at. And you don't have to go to the place you're looking. You can also scroll around in a map or search. Another thing that you might be interested in if you're interested in geology is a recent publication called Deep Oakland by Andrew Alden, who's also a member of the Northern California Geological Society. And this is a great introduction to the geology of the Bay Area, focusing on Oakland in particular. And he talks not just about geology, but the interaction of the human story, the settlement by both the Native Americans and Europeans, and how they interacted and used the geology in different places. And if you have a strong technical bent, the Northern California Geological Society published a volume through the Geological Society of America on the regional geology of Mount Diablo. That was published, I think, in 2022. Can't remember, 2021 maybe, I can't remember. And that's mostly technical papers of the mountain, but there are some papers in there, such as one on the Black Diamond mines that give more of a historical and general geological description. And finally, if you're interested in geology in general, I would suggest you check out the Northern California Geological Society's website and consider joining us. We meet 9 times a year in Orinda and have a newsletter for our members. And we're a group of both very technical geologists, as well as people, high school teachers and community college teachers, and just some people with a general interest in geology. And I think that's all I have today for you. With that, I will be happy to take questions.
Okay. Thanks, Don. As far as old school paper is concerned, Don mentioned our bookstore here at the museum, so I'll be shameless promotion for our bookstore. We have a lot of material on Mount Diablo that you can come by and take a look at. Don, your fan club checked in. A number of people from the Northern California Geological Society said they were interested and were enjoying the program quite a bit. So I've got a couple questions for you. And here's the big one. I mean, and this is the most popular question, I think, on Mount Diablo. It certainly was this morning. Can you go over the volcanic origin of Diablo, if it's not a volcano?
Thank you, Dan. I can do that. So to reiterate, Mount Diablo is not itself a volcano, but there are volcanic rocks exposed on Mount Diablo, primarily at the top of the mountain. I think I have a slide I can go to here that will illustrate why we know that the volcanic rocks on Mount Diablo did not form at Mount Diablo. I mentioned in the talk that if you look carefully at some outcrops where it's more clear, the volcanic rocks there, which have been altered to greenstones today, so they've been buried tens of kilometers deep and heated and altered to different minerals, but the shape of the rock bodies were preserved. And we can tell that those rocks started life as pillow basalts. I have here in the lower right a picture I took from Maui a few years back, the north shore of Maui, which has been uplifted by different means, what these pillow basalts look like. We have these big lumps. There's a person in the distance there. These would make nice stools you could sit on, these pillows. They give you a sense of the size. And the way they form, there's a cartoon here in the lower left where where magma, liquid rock comes out, oozes past prior sediments, and when it comes into the contact with seawater, as you can see here, the outside of the extruding body immediately quenches and crystallizes because the water is very cold relative to the 1,000-degree magma. And so it creates these bulbous shapes And that's what we can see preserved here. And then maybe to illustrate the point more, I would back up, yeah, to this, where are we? To this diagram here. So those lavas were extruded in a place like a spreading center in the middle of the ocean. So given the rates at which oceanic subduction occurs, that and the age of those lavas on the mountain today, that spreading center was probably thousands of kilometers out to sea, probably far west of where Hawaii would be today. And it traversed most of the ocean before being moved down into the crust. And then, as I showed in this slide here, scraped off the bottom of the crust and pushed up into the top of the mountain. And so the mountain is an anticline, but that's a fold with the layers that dip away from the center. But some of the rocks on the mountain were formed by volcanic processes. So
Okay.
I hope that helps.
I think it does. How about, here's one for you. How about a simple explanation for the slanted layers on Diablo?
A simple explanation. Okay.
Simple explanation.
I guess the simplest analogy I stretch back here would be folding of a rug. So if you imagine a rug as a layer similar to a layer of rocks, and you push sideways on the rug, it will wrinkle into ridges and valleys, if you will. And if you then were to slice those layers by erosion, as has been done at Mount Diablo, so this layer might have originally gone over the top, we slice it across, and we get the folding of the layers. And this process continues today. Most of the earthquakes happening in Northern California are happening of rocks sliding past one another, with those to the west moving farther north. But some of the earthquakes in California are related to this folding, and that can be seen in what we call differential GPS data. So if you take GPS measurements of specific fixed places, and you do that repeatedly over 20, 30 years, you'll find that those are moving. And in some places, they're moving by being folded together.
I like the rug explanation. That was pretty good.
I was going to go with phone books, but maybe
the rug works. That was good. Speaking of kind of the slanted layers, those kinds of things, how do you think that the geology on Diablo would have affected the indigenous populations? What were they able to take advantage of given that? And what would they have been hindered by given that?
Well, I'll start off by saying that I'm outside my expertise. But two things come to mind. One thing I have observed and have discussed on field trips are the grinding pots. And these are, on Diablo, as far as I know, they're only found in the Eocene sandstone. And this image on the left is taken from the Rock City area near there's kind of an upper parking lot at Rock City and a lower parking lot. And if you go in between those two parking lots and go down into the trees, you'll find this outcrop where these holes have been ground by hand into the outcrop. And the Native Americans, in my understanding, it was primarily the women, used these. Well, first of all, they had to create them, I assume by grinding one rock against another. And then they used them as mortar and pestle, basically. They would grind acorns within these pots. And then that was used as a staple of their diet, with treated and ground and treated acorn flour. And I think this sandstone worked out well for that, because it's hard enough to grind the acorns, but it's soft enough that they could grind these pots. It's also very uniform in character. I think many of the other layers at Mount Diablo would crumble into bits and wouldn't work well. The other thing that comes to mind is Mount Diablo has a lot of natural springs, sort of halfway down the mountain, or a little above halfway, depends where. And that's because the rocks at the top of the mountain, as Bruner pointed out, are highly fractured and broken. And so rain falling on the top of the mountain quickly gets absorbed in those fractures. But as the water gets lower down on the mountain where there's thicker clay units, the water is forced to the surface in springs. The ones I'm most familiar with, well, there's a road east, if you go east of Curry Point on Curry Canyon Road and then head north on Frog Pond Road, you come to a pond, which was a cattle pond built at one of these springs. And on the north side of the mountain, if you go out Burma Road from Juniper Campground, and this is a long hike, so I know it from mountain biking on the mountain. Go out Juniper Campground, past Juniper Campground on Burma Road, you'll come to a series of springs where I assume ranchers have actually built concrete cisterns or basins that water is flowing into constantly. And these were originally, I'm sure, used to water cattle. And I believe the park department, somebody has put goldfish in them today. So there's goldfish swimming around in those ponds.
Oh, how about that?
I presume to keep the mosquitoes at bay.
Okay, I didn't know about the goldfish. Okay, good. Um, I went to school in the South, actually in Florida, where the whole place is made of limestone. So we were used to limestone caves and sinkholes. How about Rock City? What causes the caves there?
So Rock City is a different form of caves. Usually caves form in limestone because acid rain, well, rain is naturally acidic because of the small amount of carbon dioxide in the air. When it dissolves into rainwater, it becomes carbonic acid, which will dissolve out limestone when it's above the water table. The same solutions then reprecipitate below the water table, but there's a somewhat similar process happening at Rock City. So the rainfall falls on the very porous and permeable rock and flows through the rock, but at some point comes to the surface. And as it's flowing through the rock, it dissolves some of the minerals, probably small amounts of limestone or calcite rather, as well as other minerals, other more soluble minerals in the rock. And then the water comes to the surface of the rock and it evaporates. And that evaporation redeposits those same minerals that have just been dissolved a few feet away, precipitate at the surface. So what happens is we get a resistant crust, a crust on the surface of the rock that's stronger than the rock underneath. And somehow, because stuff happens, that crust will get broken in places and then exposing the softer inside. And then either wind-blowing sand or something blasts through there, creating what are called wind caves sometimes. But so basically, it's less resistant interior to the body versus a more resistant outside.
Okay. It's always curious to me. You had that nice photograph of the Grand Canyon where everything's just layered out nice and straight, oldest to youngest at the top. Diablo's kind of the opposite of that. A lot of the older parts of Diablo are actually at the top, and the younger parts are at the bottom, right?
That is right, and that is again the what tells us that Diablo is an anticline. So I hear in a cross section, these are actually images of my small contribution to the Mount Diablo Interpretive Association's geologic map, some of these diagrams. So here I have, again, a cross section. So this is a vertical, representing a vertical slice through the earth. And the scale you probably can't read on the left is 0 to 10 kilometers. And the crest of the mountain is here. Now, Mount Diablo is particularly complicated. Where this slice goes through, actually, not right at the top, but just below the top, we have Cretaceous rocks. And then a little bit of Cretaceous rocks. And then southwest of that, we have these vertically dipping rocks that are Eocene and Miocene, and actually even get younger than that. And whereas on the northeast side of mountain, we have Cretaceous rocks, and there's a whole series of faults over there. So again, Mount Diablo is not for the understanding Mount Diablo is very difficult for the intro geologist because it's so complicated. But basically, it's the fact that there's a fold with the older rocks pushed up, and so that, and then just to complicate it even further, there's this fault right here, which is on the north side of the mountain, runs just south of Eagle Peak, if you're familiar with that on the north side. And this is actually a very old fault with mantle rocks here. So the lower part of the crust from the Great Valley has been thrust up on top of the rocks that came from the oceanic area. So it's kind of a very strong jumble almost of rocks. I hope that helps. I'm kind of walking around it because if you go to the top of the mountain and look at the diagram there, which is very well done, where they illustrate the distribution of the rocks with actual rocks, they show the mountain as an anticline, with the oldest rocks in the middle and the younger rocks on the outside, which is generally true, but in detail, it's more complicated.
Yeah, and yeah, I agree. Maybe the best thing to do is to get out, walk around, and look at everything.
But do so with a geologic map in your hand, or
true.
Yeah.
Yeah, true. We had a question, and you may need to put your viewing the future hat on for this one. But I can say the same thing. I understand. I had heard somewhere that Diablo keeps going up, and the question was, what is the future of Mount Diablo?
Well, it'll certainly be there in my lifetime. But my understanding, and I don't think that the data I've seen are not super definitive, but my understanding is Diablo is rising today at a rate of about 500 meters per million years. So a useful conversion is 1 millimeter per year is a kilometer per million years, because there's a million millimeters in a kilometer. And so oftentimes you'll see fault slip rates being listed at so many kilometers or millimeters per year. Just take that and multiply, or just convert the units from millimeters per year to kilometers per million years. So basically half a kilometer per million years. So at this diagram here, this cross section, a half a kilometer is only about this much. So in a million years, it's going to look pretty similar to what it does today, unless rates change drastically. And that seems unlikely. It is probably true that the San Andreas fault system is slowly migrating to the east, with the Hayward and some of the other faults beginning to pick up more slip through time. But as we sit today, the vast majority of the motion on the San Andreas fault system is on the San Andreas fault itself, about 80%.
So I've got a great view of Diablo out my office window, and I probably shouldn't expect that view to change at all in the near future.
No, I think you can be comfortable in your property value from that standpoint.
Got it. That's it for questions for us. And I first of all, I have to thank you, because this was one of those geologic programs where this was pretty complicated. And everything I know about Diablo is that it's pretty complicated. So thanks for taking that on for us and clearing up a lot of the questions that we have on it. And thank you all for listening this morning. If you have missed any of our earlier programs, you can find them by visiting the museum's website at museumsrv.org. Don's program from today will appear early next week. The virtual program will be taking another break in August. So join us on September the 19th. We're actually going to stay hanging out on Mount Diablo. We will learn about the navigation beacon at top Diablo. Why was it placed there? and how has it become a symbol over the years? So join us September 19th at 11:30. If you like these programs and want them to continue, we ask that you make a donation at the museum's homepage. Just click on museumsrv.org and click on the Donate Now button. We are also in need of volunteers. If you can give us some time, please contact the museum. Don, thanks again this morning. It was a great program. I hope everybody enjoyed watching it. Stay safe, and thanks for watching. Goodbye.